Okay, guys, so I'll get started. So welcome to the ECON 227 review session. Let's first introduce hypothesis. So a statistical hypothesis is a statement about the numerical value of a population parameter. The null hypothesis, denoted H0, represents the hypothesis that will be accepted unless the data provide convincing evidence that it is false. Also, for the alternative hypothesis, which is usually denoted by H1, it is the hypothesis that will be accepted only if the data provide convincing evidence of its truth, and that is usually represents the values of a population parameter for which the researcher wants to gather evidence to support. Next, we'll talk about test statistics. So it is a sample statistic computed from information provided in the sample that the researcher uses to decide between null and alternative hypothesis. So we have to collect data and calculate a sample mean x bar, and we will calculate z-score, which equals to x bar minus mu divided by sigma divided by square root of n. So for example, if the z value is 1.645, this means the chance of observing x bar more than 1.645 standard deviations above mu is only 0.05. Next, we'll talk about type 1 error and type 2 error. So a type 1 error occurs if the researcher rejects the null in favor of the alternative when, in fact, the null is actually true. So the probability of committing a type 1 error is denoted by alpha. For example, alpha equals to 0.05. And also a type 2 error occurs if the researcher accepts the null when, in fact, the null is false. So the probability of committing a type 2 error is denoted by beta. So here's a table that concludes the consequences for a test of hypothesis. Next, we'll talk about rejection region. So the rejection region of a statistical test is a set of possible values of the test statistic for which the researcher will reject the null in favor of the alternative. So if the numerical value of the test statistic falls in the rejection region, we can reject the null and conclude that the alternative hypothesis is true. And we also know that a hypothesis test process will lead to this conclusion incorrectly, which is the type 1 error only if 100 times the alpha percent of the time when null is true. So if the statistic does not fall in the rejection region, we will not reject the null. So we reserve judgment about which hypothesis is true, and we do not conclude that a null is true as we do not know the probability beta that our test procedure will lead to an incorrect acceptance of null. So this is called a type 2 error. So here we'll talk about Lintel Test. So Lintel Test of hypothesis one in which the alternative hypothesis is directional and includes the symbol smaller or larger. So for upper tailed, we use is greater than, and for lower tailed, we use less than. So here's a graph corresponding to the Lintel test. And also a two-tailed test of hypothesis is one in which the alternative hypothesis does not specify departure from a null in particular direction and is written with the symbol does not equal to. So for p-value, it is the observed significance level for a specific statistical test, and it's the probability, assuming the null is true, of observing a value of the test statistic that is at least as contradictory to the null and supportive of the alternative as the actual one computed from the sample data. So for example, if you select alpha equals to 0.05 for this test, then you would reject the null hypothesis because the p-value for the test is a definite value that is smaller than 0.05. So in contrast, if you choose the significance level to be 0.01, you will not reject the null because the p-value is probably larger than 0.01. So next we'll talk about large sample test of hypothesis about mu. So firstly, for Lintel test, we can write the null as mu equals to mu0, where mu0 is a definite value. And also, we can write the alternative as mu is smaller than mu0, or alternatively, mu is bigger than mu0. Also, for the two-tailed test, we can write the null as mu equals to mu0, which is the same as the null for the one-tailed test, and also the alternative to be mu is equal to mu0. Mu does not equal to mu0. Sorry about typo. So also for the one-tailed test rejection region, we have Z is smaller than negative Z alpha, or Z is bigger than Z alpha when the alternative states that mu is bigger than mu0. And also for the two-tailed test rejection region, we can have the absolute value of Z is bigger than Z alpha divided by 2. So here are the specific conditions required for a valid large sample hypothesis test for mu. So firstly, we have to have a random sample that is selected from a target population. And also the sample size n is large, that is n is larger or equal to 30. So this is due to the central limit theorem. So this condition guarantees that the test statistic will be approximately normal, regardless of the shape of the underlying probability distribution. Next, we'll talk about small sample test of hypothesis about mu. So firstly, for the one-tailed test, we have the null, which is mu equals to mu0. Again, this is a definite value. And also we have the alternative as mu is smaller than mu0 or mu is larger than mu0. Also, the rejection region falls into values where t is smaller than negative t alpha, or t is larger than t alpha when the alternative states that mu is larger than mu0, where t alpha and t alpha divided by 2 are based on n-1 degrees of freedom. And also for the two-tailed test, we have the null, which is the same as the one for the one-tailed test, and also the alternative as mu does not equal to mu0. And the rejection region falls into values where the absolute value of t is larger than t alpha divided by 2, and also the test statistic for this is t equals to x bar, which is the mean, and also minus mu0 divided by s divided by square root of n. So here are the conditions required for a valid small sample hypothesis test for mu. So firstly, again, you have to have a random sample that is selected from the target population. And second, you have to have the population from which the sample is selected has a distribution that is approximately normal. So here we don't have any limit on sample size. So here, large sample test is hypothesis about P. So firstly, for the one-tailed test, we again have the null to be P equals to P0. So here P stands for proportion. And also on the alternative, P is smaller than P0 or P is larger than P0. And for the two-tailed test, we have the null P equals to P0 and also the alternative as P does not equal to P0. So the rejection region is again Z is smaller to negative Z alpha or Z is bigger than Z alpha when the alternative is P is larger than P0. And the rejection region for the two-tailed test is the absolute value of Z is larger than Z alpha divided by 2. And the test statistic here is Z equals to a proportion divided by the definite value of the proportion divided by square root of P0, Q0 divided by the sample size. So here are the conditions required for the valid large sample hypothesis test for P. So you have to have a random sample that is selected from a binomial population, and also the sample size n is large. But note here, it does not require n to be larger or equal to 30, but also, but it requires that np0 is larger or equal to 15 and nq0 is larger or equal to 15. So here's the test of hypothesis about population variance. So firstly, we again have Lintel test, and the null states that sigma square is equal to sigma 0 square. So here sigma square is the population variance, and we equate it with the definite value sigma 0 square. And also the null states that sigma square is smaller than or larger than sigma 0 square. So the test statistic for this is a chi-square distribution. So chi-square is equal to n-1 times s square, which is the sample variance divided by sigma square, sigma 0 square. So here the rejection region is such that chi-square is smaller than chi-square 1 minus alpha, or chi-square is bigger than chi-square alpha when the alternative is sigma is larger than sigma 0 square. So here again, as we have mentioned before, sigma 0 square is the hypothesized variance, and the distribution of chi-square is based on n-1 degrees of freedom. So for the two-tailed test, we have a null sigma square is equal to sigma 0 square, and the alternative as sigma square does not equal to sigma 0 square. So here the rejection region is that chi-square is smaller than chi-square 1 minus alpha divided by 2, or chi-square is larger than chi-square 1 minus alpha divided by 2. So here are the conditions required for a valid hypothesis test for S square. So a random sample must be selected from the target population, and a population from which the sample is selected has a distribution that is approximately normal. Also, we have another confidence interval, which is the small sample CI for mu I minus mu 2, which is the difference between the means. And since we assume the two populations have equal variances, it is very reasonable to use the information contained in both samples to construct a pooled sample estimator for sigma square for using confidence intervals and test statistics. So here are the following. Here following are the confidence interval formulas, and we can see T alpha divided by 2 is based on n1 plus and 2 minus 2 degrees of freedom. So S square is the pooled variance, and it is simply a weighted average of the two sample variances. So note that if the two variances have the same number of degrees of freedom, which means the sample sizes are equal, then the pooled variance is a simple average of the two sample variances. So small sample one-tailed test of hypothesis for the difference between the mu's. So one-tailed test, we have to know the difference equals to D0, where D0 is the hypothesized difference between the means, which is usually assumed to be 0. And also we have the alternative as the difference is smaller than D0 or larger than D0. And we have the test statistic here, which equals to the difference between the means minus the definite value D0 divided by the square root of S square times the sum of 1 over the sample sizes. So here, rejection region, we have T is smaller than negative T alpha, or is larger than T alpha when the alternative is such that the difference is larger than the definite value, and where T alpha is based on n1 plus n2 minus 2 degrees of freedom. Also, we have the two-tailed test, which we have the same null hypothesis as in the one-tailed test, and we have the alternative as the difference does not equal to D0. So for the rejection region of the two-tailed test, we have the absolute value of T is larger than T alpha divided by 2, where T alpha divided by 2 is based on n1 plus n2 minus 2 degrees of freedom. So again, we have the conditions required for a valid small sample inference about the difference between the mu's. So the two samples are randomly selected in an independent way from the two target populations. So both sampled populations have distributions that are approximately equal. So note here, we do not require the two distributions to be normal, but we require them to be approximately equal. And also the population variances are equal. So next we'll talk about approximate small sample steps where sigma 1 squared does not equal to sigma 2 squared. So the first case is such that the sample sizes are equal and the assumption of equal population variances can be relaxed. That is, if the sample sizes are equal, then sigma 1 squared does not equal to be sigma 2 squared. So we have a formula for the confidence interval, which equals to the difference between the means plus or minus t alpha divided by 2 times square root of the sum of s squares and divided by the sample size. Also, we have the test statistic where we state that the null to be the difference between the means is 0. So t is equal to the difference between the means and minus d0 divided by square root of s1 plus s1 squared plus s2 squared divided by the sample size. So t here is based on v is equal to n1 plus n2 minus 2, which equals to 2 times n minus 1 degrees of freedom. And next, we will have the case where the sample sizes are unequal. So here the confidence interval formula turns out to be the difference between the means on time plus minus t alpha divided by 2 times square root of the sum of sample variances divided by the sample size. Also here again, we have the test statistic where we assume the null to be the difference between the means is equal to 0. And also t is equal to the difference between the means minus t0 divided by the square root of the sum of squares divided by their own sample sizes. And so t here is based on degrees of freedom equal to v equals to this complex formula. So the value of v will generally not be an integer due to this complex formula. So we have to round v down to the nearest integer when using the t-table. Next, we'll talk about paired difference test of hypothesis for mu d equals to the difference between the mu's. So firstly, for the Lintel test, we have the null mu d is equal to d0. And for the alternative, mu d is smaller than d0 or larger than d0. And the test statistic for a large sample where z equals to d bar minus d0 divided by sigma d divided by square root of n. So here d bar stands for the difference between the mu's. And also again, we have the rejection region where z is smaller than negative z alpha, or is z is larger than z alpha when the alternative mu d is larger than d0. So for the two-tailed test, we have the same null as in the one-tailed test, and also the alternative states that mu d does not equal to d0. And so the test statistic for large sample, so z is equal to d bar minus d0 divided by sigma d divided by square root of n. So here the rejection region is such that the absolute value of z is larger than z alpha divided by 2. So we have sample confidence interval for the difference between the mu's. And also for a large sample, we have d bar plus or minus z alpha divided by 2 times square root of sigma squared d divided by n. And again, for small samples, we replace z alpha divided by 2 by t. And also we times sample variances instead of the population one. So where t alpha divided by 2 is based on n minus 1 degrees of freedom. So here are the conditions required for valid large sample inferences about mu d. So a random sample of differences is selected from the target population of differences. And also the sample size n is large, which means n is larger or equal to 30. And again, this is due to the CLT. So here are the conditions required for valid small sample inference about mu d. So again, random sample of differences is selected from the target population of differences. And also the population of differences has a distribution that is approximately normal. So next we'll talk about properties of the sampling distribution of the differences between the estimates for proportions. So the mean of the sampling distribution of the estimates for the differences between the proportions is P1 minus P2. So this means that the expectation of the estimates estimated differences is equal to P1 minus P2. So which is the actual difference between the population proportions. So the estimated value is an unbiased estimator of P1 minus P2. So here we also have the standard deviation of the sampling distribution to be square root of the sum of P1 Q1 and divided by N1 plus P2 Q2 divided by N2. So if the sample sizes N1 and N2 are large, then the sampling distribution of the estimated differences will be approximately normal. And next we'll talk about large sample confidence interval for the difference between the proportions. So the CI is equal to the following formula. And also for the conditions required for valid large sample inferences about the difference between the proportions. So the two samples are randomly selected in an independent manner from the two target populations. And also the sample sizes N1 and N2 are both large, so that the sampling distribution of the estimated difference will be approximately normal. So this condition will be satisfied if both N1 P1 and N1 Q1 and N1 P2 and N1 Q2 are all larger or equal to 15. So next we'll talk about large sample test if hypothesis about the difference between the proportions. So firstly, for the Lintel test, we have the null to be the difference is equal to 0. And for the alternative, we have P1 minus P2 is smaller than 0 or larger than 0. And also the test statistic for small sample is such that Z is equal to the difference between the estimated values divided by their standard deviation. So here the rejection region falls in values where Z is smaller than negative Z alpha or Z is larger than Z alpha when the alternative is the difference is larger than 0. So secondly, for the two-tailed test, we have the null to be the difference is equal to 0, the same as the one-tailed test, and also the alternative to be the difference does not equal to 0. So here we have the rejection region where the absolute value of Z is larger than Z alpha divided by 2. So here we have determination of sample size for estimating the difference between the mu's. So to estimate the difference with a given sampling error, which is denoted by SE, and with confidence interval 1 minus alpha, we can use the following formula to solve for equal sample sizes that will achieve the desired reliability. So here N1 equals to N2, which thus equals to Z alpha divided by 2 squared times the sum of the population variances divided by the sampling error SE squared. So here are the large sample two-tailed test of hypothesis for the difference between the proportions. So N1 equals to N2 equals to Z alpha divided by 2 squared times the sum of P times Q divided by the sampling error squared. And we have to substitute estimates for values of P1 and P2 before solving for the sample size. So usually if the question is not specifically specified, we can just say that P1 equals to P2 equals to 0.5. So here we have independent sampling F-test for equal population variances. So first we have Lintel test where the null is such that the 2 sigma squared are equal, and the alternative is such that sigma 1 squared is smaller than sigma 2 squared, or sigma 1 squared is larger than sigma 2 squared. And also we have the test statistic where F equals to S2 squared divided by S1 squared, or F is equal to S1 squared divided by S2 squared. So it is for the alternative where sigma 1 squared is larger than sigma 2 squared. So the rejection region for one-tailed test is such that F is larger than F alpha, where F alpha is based on V1, which is the numerator degrees of freedom, and V2, which is the denominator degrees of freedom. So they are the degrees of freedom for the numerator and denominator sample variances, respectively. And also we have the two-tailed test where the null is the same and the alternative is basically sigma 1 squared does not equal to sigma 2 squared. And also we have the test statistic where F is equal to S1 squared divided by S2 squared. And when S1 squared is larger than S2 squared, or we have S2 squared in the numerator when S2 squared is larger than S1 squared. And also the rejection region is such that F is larger than F alpha divided by 2. So here are the conditions required for a valid F test for equal variances. So both sampled populations are normally distributed, and also the samples are random and independent. So here's a ANOVA table. And we have ANOVA F test to compare K treatment means. So here we have the null with all means equal to each other, and also the alternative that states that at least 2 treatment means differ. So the test statistic is F equals to MST divided by MSE. And also we have the rejection region where F is larger than F alpha, and F alpha is based on K minus 1 numerator degrees of freedom, which is associated with MST, and N minus K denominator degrees of freedom, which is associated with MSE. So here we'll talk about simple linear regression model. So simple linear regression model usually has the formula yi is equal to beta 1 plus beta 2 xi plus ui, where I equals to 1 to n. And so n is the sample size and y and xi are the observations. So yi is usually called the dependent variable, with xi being called the independent variable. So both betas are unknown parameters, and ui is the unobserved error term. And also beta 2 is the slope. It can be positive or negative, and beta 1 is the intercept. So next we'll talk about ordinary least square. So it is an estimator for the slope and the intercept of the regression line. And also the estimators beta 1 hat and beta 2 hat are to minimize the SSE, which is the sum of square of error. And also both estimators are the ordinary least square estimates of the population parameters beta 1 and beta 2. So here we have the formulas for beta 1 hat and beta 2 hat, with beta 1 hat equals to y bar minus beta 2 hat x bar. And also we have beta 2 hat equals to the sum of xi minus x bar times yi minus y bar divided by the sum of xi minus x bar square, which is basically the variance of x. So here we have the model assumptions. We have a total of 4 assumptions, and the first one states that linearity in parameters, which is the population model is linear in its parameters. And secondly, we have 0 conditional mean. So the expected value of the error term is 0, conditional on all values of the explanatory variable. And thirdly, we have homoscedasticity. So the error term has the same variance conditional on all values of the explanatory variable. And fourthly, we have normality, which the error term is independent of the explanatory variables and is normally distributed. So here we can estimate sigma square, which is the population variance, when the error term is unknown. So the sample variance for ui s squared is equal to SSE divided by n minus 2 and equals to the sum of y minus y bar y hat I squared divided by the degrees of freedom, which is n minus 2. So note the sampling distribution of beta 2. So the sampling distribution of the least square estimator beta 2 hat, which is the slope, is such that it is distributed normally and with a mean of beta 2, the population estimator, and also with the variance of sigma squared divided by the sum of xi minus x bar squared, which is basically the variance of x. So next we'll talk about the test statistics. And for the one-tailed test, we have the node to be the slope is equal to 0. And for the alternative, we have the slope is larger than 0 or smaller than 0. So basically, we're testing the significance of the slope. And the test statistic is as follows. T is equal to beta 2 hat divided by s divided by the sum of xi minus x bar squared, which is the square root of the variance of x. So rejection region, we have the absolute value of t is larger than negative t alpha divided by 2, where t is based on n minus 1, n minus 2 degrees of freedom. And also for the two-tailed test, we have to know beta 2 hat is equal to 0, and the alternative beta 2 hat does not equal to 0. So we have the rejection region where the absolute value of t is larger than negative t alpha divided by 2, and t is based on n minus 2 degrees of freedom. Next, we'll talk about coefficients of correlation. So it denotes how strong is the linear relationship between two variables, and also the sample correlation coefficient denoted R with values ranging from -1 to +1, and it also measures degrees of association. However, it does not indicate any causal relationship. So basically, it's just a number indicating the linear relationship, but it does not contain any cause-effect relationship. So here we have a test for linear correlation. So the population correlation coefficient is denoted by the simple rho, which is estimated by the corresponding sample statistic R. So firstly, we have the Lintel test, where the null states that rho is equal to 0. And also we have the alternative where rho is larger than 0 or is smaller than 0. So the following is the test statistic. And we have rejection region where t is larger than t alpha or t is smaller than negative t alpha. So this should be the two-tailed test, and the null is rho equals to 0, and the alternative is rho does not equal to 0. And we have the rejection region falling to the absolute values of t where it is larger than t alpha divided by 2. So here t is based on n minus 2 degrees of freedom. So we have coefficient of determination, and it measures the contribution of x in predicting y, and it also represents the proportion of the total sample variability around that is explained by the linear relationship between y and x. So it's basically the squared value of the R we have seen in the previous slide. And R squared is always between 0 and 1, since R is between -1 and +1. So we can also use the model for prediction. So to use the model to predict a new individual y value for a given x value, we can write this as y hat is equal to beta 1 hat plus beta 2 hat times a specific value of xi. So we basically can plug into a specific value of xi, and we can get a value for y hat, which is the estimated value for y. So sampling error for the predictor of an individual new value of y at x equals to xi equals to the following one. And sigma is the population standard deviation of the error term. And since sigma is usually unknown, we can replace it by s. So a 100 times 1 minus alpha % prediction interval for an individual new value of y at x equals to xi is equal to y hat plus or minus t alpha divided by 2 times the standard deviation of y. And also here, t alpha divided by 2 is based on n minus 2 degrees of freedom. So here we have the first practice problem. And so the question states that in fitting a least square line to n equals to 20 data points, the following quantities were computed. So basically we have x is equal to 83, and the sum of yi minus y bar squared is equal to 198. And the sum of xi minus x bar times yi minus y bar is equal to negative 108, and x bar is equal to 2.3, and the mean of y is equal to 35. So we have the following questions where we have to find the simple linear regression model and graph it, and also calculate SSE and S squared. And lastly, we have to find a 95% confidence interval for the slope, and also interpret this estimate and find a 90% prediction interval for y when x is equal to 50. So I'll give you guys 10 minutes to do this. So for the ones that will be watching the recording in the future, you can also take this time to try this question. Yeah. I'll share with you the solutions after 10 minutes. Now we'll talk about the solutions for practice problem 1. So for part A, we are asked to find a simple linear regression model. So we basically have to find the estimates for beta 1 hat and beta 2 hat. So by using the formula stated in the previous slides, we have beta 2 hat is equal to minus 1.301, and also for beta 1 hat, we have it is equal to y bar minus beta 2 hat times x bar, which equals to 37.993. And also, we can state a simple linear regression model in the form with y equals to 37.993, which is the value for the intercept, and minus 1.301 xi plus ui. So for part B, we are asked to graph the least square line and specify the slope and intercept in the graph. And so here we basically have the slope is equal to beta 2 hat, which we have just calculated in part A. So it is equal to negative 1.301, and we have the intercept equals to 37.993, and it is the intercept on the y-axis. And for part C, we are asked to calculate SSE. So here we can plug in the values into the formula with SSE equal to SSYY minus beta 2 hat SSXY. So basically it's the variance of y minus beta 2 hat times the sum of xi minus x times yi minus y. So by plugging the values we have stated in the question, we have SSE is equal to 57.4699. And also for part D, we are asked to calculate sample variance of error term, which is S squared. So we can directly use the formula, which is equal to SSE divided by n minus 2. And we can use the value for SSE calculated in part C divided by the sample size, which is 20 minus 2. And we have a degree of freedom, which is equal to 18. Thus, we have S squared is equal to 3.1928. And also for part E, we are asked to find a 95% confidence interval for the slope and also interpret the estimate. So we have df is equal to 18 as we have calculated in part D. And also we have to calculate the critical value of t, so which is equal to 2.101. So the 95% CI for the slope is basically equal to the estimate for beta 2 hat plus or minus the critical value of t times square root of MSE divided by variance of x. So basically the CI equals to minus 1.713 to minus 0.889. So lastly, we are asked to find a 90% prediction interval for y when x is equal to 15. So here we have x equals to xi is equal to 15, which is a definite value. So y hat is equal to the value for the intercept plus the estimated value for the slope times 15, which is the definite value of xi. Thus we have y estimated value is equal to 18.4747. And since here we are using alpha is equal to 0.1 because of the 90% prediction interval, we can write the critical value of t equals to 1.734, and with the standard deviation equal to this formula, and we have it is equal to 3.09. And thus we can write the 90% prediction interval as 18.4747 plus or minus the standard deviation value times 3.09. So we thus have the prediction interval finally equals to 13.114 to 23.85. So here's another practice problem. So in this question, we have two variables. The first one is income, which is in $1,000 and is denoted by yi. So this is our dependent variable. And also we have age, which is in years and is denoted by xi, so that's our independent variable. So here's a table. You can take a screenshot of it if you want to. And so the question states that the mean income is $49.05556 and the standard deviation in income is $16 and the mean age is 39.94 years and the standard deviation in the ages is 10.8382 years. So part A asks test at a 5% level on whether the mean age is significantly less than 42. And part B asks give a 90% confidence interval for the mean age, and also give the theoretical requirements for the use of the distribution and the formula that you use. And also for part C, it requires to find the regression model when income is regressed on age. So basically the sentence means income is the y variable and is the dependent one, and also age is the independent variable, which is usually denoted by xi. So for part D, it asks, are ages and income significantly correlated using the test of correlation? And alpha here is equal to 5%. And so for part E, we have to find the 95% confidence interval estimate for the marginal contribution of age to income. And on the average, how much more does a person make on this year's birthday than on last year's birthday? So again, I'll give you guys 10 minutes for this one, since it takes a quite long time to do this one. So yeah, I'll share with you the solutions after 10 minutes. So now I will talk about the solutions for part 2. So basically for the first question, we are asked to test at 5% level whether the mean age is significantly less than 42. So we'll write the hypothesis as now is mu is larger or equal to 42, and the alternative as mu is smaller than 42. So basically we can plug in values for the test statistic equals to x bar minus mu divided by sx divided by square root of n, which is approximately equal to minus 0.8047. And since we are testing at the 5% significance level, and also the DF value is 18 minus 1 equal to 17, we have the t critical value equal to negative 1.74. And also since the t critical value is smaller than our test statistic, we do not reject the null. So our conclusion is that the mean age is not significantly less than 42. And for part B, we are asked to give a 90% confidence interval for the mean age, and also give the theoretical requirements for the use of the distribution and formula that we use. So here, the 90% CI for the mean age is basically x bar plus or minus t critical value times sx divided by square root of n, where n is 18. And we thus have the CI equal to 35.4994 to 44.3894. So the theoretical requirements is such that the sample size is smaller than 30. So we can use the t distribution, and we have only one sample that is age. So for part C, we are asked to find a regression model when income is regressed on age. So basically, we plug in values into the formulas for the estimate value for beta hats, and we have beta 2 hat is equal to 1.1418, and beta 1 hat is equal to 3.45. So we have y equals to 3.45 plus 1.14 times xi plus ui. And for part D, it asks, are age and income significantly correlated by using the test of correlation? So here we state the null to be rho equals to 0, and we calculate the R value, which equals to beta 2 hat times the sum of xi square minus nx bar square, which is the variance of x, and divide by the variance of y. So here we have the result as R equals to 0.759. And also since the sample size is 18, we have the DF equal to n minus 2, which is equal to 16. And here we calculate the t critical value, which equals to 4.663. The t critical value is such that it is equal to 2.120. So since the t critical value is smaller than 4.663, we can reject the null, and to conclude, ages and incomes are significantly correlated. And so for part E, it asks to find a 95% confidence interval, estimate for the marginal contribution of age to income, and also on the average, how much more does a person make on this year's birthday than on last year's birthday. And so we first calculate the value for SSE, which is equal to 1,900, 13.524353, and we can thus calculate the value for the 95% CI, which we can plug in values for beta 2 hat plus or minus t critical value with alpha divided by 2 and n minus 2 degrees of freedom times the square root of NSE divided by variance of x. So we have the CI equal to 0.623 to 1.6606. And so here we have the third practice problem, and we have the table here, and also you can take a screenshot if you want to, and we have the third table 3, which is a descriptive statistics. And so basically the first question asks, regress the variable total on the variable durable, and also find simple linear regression model and interpret the slope inverse. Also, part B asks for find the prediction model and predict the total price index when the price index durable goods is 98.3, so it is a definite value. And also to test whether the durable goods index is significant for predicting the total price index using the test of slope. And so it can also test using alpha equals to 5%, and also to find a 90% prediction interval. And for part E, what proportion of the variation in the total price index is explained by the regression relationship with the durable goods index. And also lastly, we have to use the simple linear regression model opting to find the residual for the year 2000. So I'll also give 10 minutes for this one, and we'll share the solutions with you after 10 minutes. So I'll talk about the solutions for practice problem 3. And so here we have the solution for part A being total hat is equal to beta 1 hat plus beta 2 hat durable plus ui, which is the arrow term. And by using the formulas, we have beta 2 hat is equal to 1.20, and also we have the value for beta 1 hat is equal to y bar minus beta 2 hat times x bar. So it is basically equal to minus 24.87. So we can thus write the linear regression model as total hat is equal to minus 24.87 plus the slope times the durable and plus ui. So we can interpret the slope as beta 2 hat is equal to 1.20, and this indicates that the covariance between total and durable is positive, and also the slope is also positive. So total and durable are positively correlated. And also for part B, we have the total hat when durable is equal to 98.3 is equal to 93.64. So also the prediction model is such that total hat is equal to the intercept plus the slope and times durable, but without the arrow term. And so for part C, we have it known as beta 2 hat is equal to 0, and the alternative being beta 2 hat does not equal to 0. So S squared, as we have seen in the previous slides, it is equal to SSE divided by n minus 2. And so basically we plug in values and we get S squared is equal to 34.57. And by square, and we take the square root of S squared, we have S is equal to 5.88. So because the DF is equal to 18, we have the critical value of T is equal to 2.101. So we can write the test statistic as equal to 6.224. And since T is smaller than 6.224, we can reject the null and conclude that the durable goods index is significant for predicting the total price index. And so for part D, we are asked to find a 90% prediction interval. So here we first calculated standard deviation, which is equal to 6.02. And also since the DF is n minus 2, which equals to 18, so the 90% PI is equal to 98.2985, which equals to the y hat value when xi equals to 94.7, and plus or minus the critical value of T times the standard deviation, which finally equals to 78.85 to 99.74. And so for part E, what proportion of the variation in the total price index is explained by the regression relationship with the durable? So first we calculate MSE, which is equal to S squared, and it is calculated in the previous parts, which is 34.57. And also SS total is equal to 1961.318. And we can write in an ANOVA table and get R squared equal to SSR divided by SS total, which is equal to 0.68. So basically, this is saying that 68% of the variation in the total price index is explained by the regression relationship with the durable. So for part F, use the simple linear regression model we have obtained to find a residual for the year 2000. So here we have residual is equal to ui hat and is equal to y minus yi hat. So here we have yi is the observation value, which is 96 minus on the estimated value for yi, which basically we can plug in xi is equal to 100.8, and thus we have the residual being equal to minus 0.65. So this is the first practice problem. So it has 4 parts, so I'll probably give you guys about 8 minutes to do this, and we can talk about the solutions. Well, let's go through the solutions for the problem 4. So for part A, it asks what's the proportion of significantly different from 80% and test using alpha value equals to 5%. So we can first calculate the actual proportion, which is equal to x divided by n, and is equal to 0.8063. And we can write the hypothesis as the null being equal to p equals to 0.8. And also for the alternative hypothesis, we have p does not equal to 0.8. So since the sample size here is very large, we can use the test statistic, which is equal to 0.37. And also for the critical value of we have alpha divided by 2, and here alpha is 0.05. So we have the value equals to 1.96. So since the critical value is larger than the test statistic, we do not reject the null, and we can conclude that the proportion is not significantly different from 80%. And also for part B, we have find the p-value for the test of part A. And so basically we can just plug in the values. We can just find the values in the set table and conclude that the p-value here is 0.71. And also for part C, we have to find a 90% confidence interval for the proportion of dairy farms with calf dehorning. So here we have alpha is equal to 10%, and so z is equal to 1.645. So here a 90% CI would be equal to P, which is this proportion, plus or minus z value, and times the square root of P times Q divided by N, which is the sample size. So here we have the CI equals to 0.77 until 0.83. So for the last part, how large a sample would be needed to establish a 92% confidence interval for the proportion if the margin of error is to be 1.6 percentage points. And so here basically the margin of error stands for the sampling error, and we can use the formula as in the previous slide, and we can calculate based on alpha is equal to 8%, which means that value is equal to 1.75. And so here E is equal to 0.016, and the proportion is basically 0.86. So the sample size would be Z squared times PQ, and also divided by E squared, so which is equal to 1869. So here we have to note that whenever we get a sample size that has decimals, we can always round it up instead of round down. So here's the fifth one. And this is the first table. You can take a screenshot if you want to. And we have the two parts here. And I'll give 5 minutes for this one. So let's see the solutions. So for part A, it asks test whether there is any significant difference in the means. Use alpha equal to 0.05. So here we have firstly the ANOVA table, and SS total is equal to 6150.4, and also SS treatment is equal to 1419.6. So we write the null as the three treatment means are equal, and the alternative as at least one mean is significantly different. And also we can write the test statistic as MST divided by MSE, which equal to 1.8, with the critical value of F equal to 3.885. Since we have that the critical value of F is larger than 1.8, which is the test statistic, we do not reject the null, and we can conclude that there is no significant difference in the mean of the record percentage for student drivers in the three groups. And so for part B, it asks to conduct a test of hypothesis to determine if the standard deviation of group 1 is bigger than 18, and use alpha equal to 0.05. And so we have the null as sigma equal to 18, and also the alternative as sigma is larger than 18, so that's a Lintel test. And we can write the test statistic as the chi-square distribution one, and we can have it equal to 4.1198. And since the alpha is equal to 0.05, the F is equal to 4, we have the chi-square critical value equal to 9.488. So since the critical value is larger than the test statistic, we do not reject the null, and we can basically conclude that the standard deviation of group 1 is not significantly bigger than 18. So that is the sixth problem. I'll give you guys about 5 minutes for that. I'll talk about the solutions now. So for part A, it asks, is there sufficient evidence to state that a proportion of salmonella in the region's water is bigger than the proportion of salmonella in the region's wildlife? And we can use alpha equals to 5% to make our decision. So firstly, we can calculate the proportion of salmonella in the region's water, which is P1's hat, and it is equal to 0.15. And also we can calculate the proportion of salmonella in the region's wildlife, which is P2 hat, and it is equal to 0.052. So we can write the null as the difference between the proportions equals to 0, and the alternative as the difference between the proportions is larger than 0. And since alpha is equal to 5%, we have the critical value for Z is equal to 1.645. And here we have the test statistic as 4.26. So since the test statistic is larger than the Z critical value, we can reject the null and conclude that there is sufficient evidence to state the proportion of salmonella is bigger in the region's water than in the region's wildlife. And also for part B, we have to construct a 99% confidence interval for the proportion difference of salmonella between the region's water and the region's wildlife. And so basically we can use the formula and write 99% CI as the difference between the estimated proportions plus or minus Z alpha divided by 2 times the square root of the sum of PQs divided by their own sample size. So we have the result of 0.039 to 0.157. So here's the last practice problem. So again, I'll give you guys 5 minutes to do this one, and we'll talk about the solution. I'll talk about the solutions now. So for part A, it asks test whether the standard deviations in service rating score are significantly different in female and male at the 5% significance level. So here, we can let sigma 1 represent the standard deviation of male sample and also sigma 2 represent the standard deviation of female sample. And we can write the null hypothesis as both sigmas are equal, and also the alternative as the two sigmas are not equal. So here the test statistic is equal to S2 squared divided by S1 squared, which is equal to 1.065. And since the degrees of freedom of the numerator is 14 and for the denominator is 9, and also the alpha level is equal to 0.05, we have the F critical value equals to 3.21. Since our test statistic is smaller than the critical value of F, we do not reject the null, and we can conclude that the standard deviation in service rating score are not significantly different in female and male. Also for part B, it asks test whether the mean in service rating score for male is significantly greater than a mean in service rating score for female at a 10% significant level. And so we can let mu1 be the mean of the male sample and mu2 be the mean of the female sample. And we can write the null as the difference between the means is equal to 0. And also the alternative as mu1 minus mu2 is larger than 0. So since the sample sizes for males and females are unequal, we have to use the complex formula for the degrees of freedom. And we can calculate that the degrees of freedom is equal to 19. So the critical value for T is equal to 1.328. And also we can calculate the test statistic equal to 1.685. And since our T critical value is smaller than our test statistic, we can reject the null and conclude that the mean in service rating score for male is significantly greater than the mean for female. Okay, so that's the end of our review session. Thank you for coming, and I'll end the review session right now.